right, welcome back everyone. Last video we began section 4.5 on a integration technique called the substitution rule, which is really more of a technique than it is a rule because it does not work for every integrand. It works generally for integrands of a certain type. Okay. Today we're going to go over some suggested steps for integrating this type of function, and then we'll do some examples of that. And I will emphasize again that these are suggested steps. These are not hard and fast rules. Integration is really more of an art than it is a set of rules like differentiation was. Generally, if I want to integrate, then my goal is to get the integrand into the form of a function that I have a rule for, therefore know how to integrate, or to recognize the integrand as the derivative of another function. Those are the primary two techniques. But it takes practice. It takes working with derivatives and integrals a lot to get to where you can do that. So I suggest you do several of these, do a number of them, take your time on them, and you'll begin to see the different forms that certain integrands come in and get better at integrating. Okay, so let's go over these steps for integrating a function of this form. Function of the form f prime. Excuse me. F prime of g of x times g prime of x dx. Okay. So if I see this integrand, it is a composite function, and it is being multiplied by the derivative of this inside portion here. If that is the form of my integrand, then generally I will want to integrate by substitution. So here are the suggested steps. If I'm given an integrand of this form, f of g of x, or f prime of g of x if you prefer, then let's see. Let's assign the variable u to the g of x portion, to that inside portion of the composite part. I can use that then to find du. So I can differentiate both sides of the equation that I set up in step 1 and find du. So how I would think about that is if u is equal to g of x, then du dx is equal to g prime of x. Then if I multiply both sides by d of x, I get that du is equal to g prime of x times dx, which is what we have here. Now that I have those portions, I can substitute. So I can replace g of x with u, and I can replace du with whatever it's equal to, g prime of x times dx. It won't always be quite that straightforward, but we can usually do something of that nature. It's very important at this step to make sure that you transform the entire integrand into terms of u. So there are no x's left in your integrand. I don't want both variables to be left. I want to change it to where, remember, this term here, this dx term, tells me what variable I'm integrating with respect to. So I want to change everything into terms of u because I'm replacing that dx term with a du term. So I want to make sure there are essentially no x's left. everything is in terms of u's. Everything is in terms of u. At that point, I want to look at my integrand and say, well, do I have a rule that allows me to integrate? If so, then I need to apply that rule. Go ahead and integrate. If not, then I have to rethink. I have to substitute a different way or use a different technique for integration. But if I am allowed to integrate there, then I have an integral in terms of u, not x. So at that point, I need to back substitute. So I need to recall that u is equal to g of x, and I need to use that knowledge to rewrite the integral in terms of that. Okay? So let's do some examples. Let's say that I have this function. Let's say I have this function f times 5x plus 1 to the 10th power. And I want to integrate that with respect to x. Okay? Now, technically, I could expand this. I could multiply 5x plus 1 to by itself 10 times, but that would be a whole lot of work. I don't really want to do that. I would rather use a technique of substitution to integrate this. So let's recognize that this is a composition. This I could write as f of g of x, where that f of x portion, or that g of x portion rather, is this. It's what is inside the power of 10. Okay? So now that I have that, I am going to assign u. I'm going to say u is equal to g of x, which is 5x plus 1. Once I have u, I can find du. du dx is equal to the derivative of 5x plus 1, which is 5, which means that du is equal to 5 times dx. So I have an expression for u, and I have an expression for du. I'm actually going to call this blue term. Maybe I'll notate this one in green. Okay. So at that point, I can substitute. The integral of 5 times 5x plus 1 to the 10th power dx. All right, let's see here. I know that my 5x plus 1, that's my u term. How about du? du is 5 times dx. Well, I have a 5 multiplied by 5x plus 1 to the 10th multiplied by dx, because it does not matter what order I multiply things in. I know that that is my du term. So I can rewrite this. This is equal to the integral of u to the 10th times du. Okay? And at this point, I have to look at it and go, well, can I integrate? It appears that I have rewritten this completely in terms of u. There are no x's left. And I do have a rule for anti-differentiation that allows me to find that indefinite integral. So now I can apply that rule. So the integral of u to the 10th du is equal to u to the 10 plus 1, which is 11, times 1 over 11 plus c. So I've applied my rules of anti-differentiation. My last step is I need to back substitute. So I need to recall that u I called 5x plus 1. So I'm going to resubstitute that into my integral here. So it's equal to 1/11 times u, which is 5x plus 1 raised to the 11th power plus c. So that expression is the integral of 5 times 5x plus 1 to the 10th power plus c. Okay, let's do another example. Let's say I want to find the integral of the cosine cubed of x times the sine of x dx, which anytime I see a exponent on a trigonometric function, I like to rewrite it. This means cosine of x cubed times the sine of x dx. And now I can recognize this as a composite portion of the function. I can recognize this as f of g of x, or f prime of g of x if you prefer. They're both compositions, where my g of x term is what's inside. It's the cosine of x. So now that I have that, I can do step 1. I can say that u is equal to that g of x portion, which is the cosine of x. Okay, so that I have the cosine of x is equal to u, which means I can use that to find du. Du, I'm going to differentiate both sides of the equation with respect to x. Du dx is equal to negative sine of x. Now, if I multiply both sides of the equation by dx, I get that du is equal to negative sine of x dx. Okay, so I have u and I have du. At this point, I want to substitute. Integral of the cosine of x cubed times the sine of x dx. I know, as we've stated, that this portion is u. What about du? This portion is almost du, but it differs by a sign. How could I fix that? What if I multiplied both sides of this equation by -1? Well, then I would get that negative du is equal to the sine of x dx, which happens to be right here. So it looks like that portion of the integrand is actually negative du, not just du. So I can rewrite this. I can substitute. It's equal to the integral of u cubed times negative du. I can look at that and make sure that all of the x's are gone from my integrand. It looks like I have substituted u's for them all. Now can I integrate? Well, this portion of the function is something that I have a rule for. This negative sign I can just pretend is a -1 multiplied by the du, so I can move a constant out front of the function. I can integrate that. So integral of u cubed negative du is equal to negative integral of u cubed du. I can apply one of my rules of anti-differentiation. So this is negative u to the 3 plus 1, which is 4, times 1 over 3 plus 1, which is 4. All of that plus c. I've applied my rules of anti-differentiation, therefore I can drop this antiderivative symbol. Okay. As a last step, I want to resubstitute. I don't want to leave that integral in terms of that variable that I created, u. So I'm going to recall that u I called cosine of x, which means that this integral is negative 1/4 times u, which is cosine of x to the 4th power plus c. Now, if I wanted to check myself, I could differentiate that. I can always check my integration by differentiating, and I should get back to my integrand. But I am not going to do so. All right, let's stop there. I'll do one more example in another video.